7.1, basic ideas. And we're talking about some basic ideas of how to manipulate so we can take the integral of some function easier. So basic ideas on integration is what it really should be called. And what I want to talk about is just being able to manipulate and remembering some basic antiderivative formulas that we could give in a list. But remember, there is no formula sheet on the test. So we have some basic integration formulas. A lot of these we know already. If we're given a constant, we add the x. If we have cosine, it's sine with anti-chain rule. Secant squared is tangent, anti-chain rule. Secant tangent is really secant. Remember, anti-chain rule. And then we have an E. Then we also have, remember, some form of where the antiderivative is sine inverse, some form where the antiderivative is secant inverse. We do have, I know we're going to need at least this one today, where we have the antiderivative given a cosecant cotangent is just negative cosecant. We know ln, where ln is the antiderivative. We know where the antiderivative is tangent inverse. So this is just a basic integration formula list, things that we have done before. So I want to go ahead and start walking through some examples. So for example 1 here, we just want to review substitution. And this is what we've done before. So it's just going to, in a sense, review it and going to have u be 3 plus 2x. Remember, we're going to take the derivative of this and we get 2. And then I'm going to multiply both sides by dx. And since I don't have a 2 to replace, I'm going to go ahead and divide both sides by 2. So now I can do my substitution, and I have in here where the dx is replaced by du over 2. And I have that the 3 plus 2x in the denominator is being replaced by u. So I'm going to go ahead. 2 more things I need to do is change my bounds. If I plug in -1 into the u function, I get 1. And if I plug in 2, I should get 7. So my new bounds are 1 and 7. And I'm going to go ahead and neaten up this du. So I'm going to pull that 1/2 of a fraction out. And I have du over u going from 1 to 7. This is then where I take the antiderivative and I'll get ln of u, and we're evaluating it from 1 to 7. And I forgot my 1/2 in front. There we go. So then I have to go ahead and evaluate this, plugging in 7. And then technically it's going to be minusing ln of 1. But remember, ln of 1 is really a value of 0, so I am ending up with this as my answer. So that's just reviewing substitution. Remember, because I changed bounds, I did not need to resubstitute. And if it was an indefinite integral, I would have to resubstitute my u value. So this one is called a subtle substitution because what I'm really going to do is kind of manipulate it first before I try to do any kind of u substitution. Because let's do, for example, if I was to let u equal, let's say it was e to the x, and then I take the derivative of this, and I get e to the x again, but that's not what I have, it just kind of makes a mess. So this is a little too early to try to do some u substitution. So what I'm going to do is I'm going to go ahead and multiply this equation by an e to the x over an e to the x. And I now have e to the x dx over e to the 2x, because I'm multiplying, and then e to the x times e to the negative x. Remember, we're adding the exponents. That would be really e to the 0, and then e to the 0, anything to raise to the 0 power is 1. So in this case, I'm now going to just make this 1. So it makes more sense now that if I do my u substitution now and let u equal e to the x, I'm going to go ahead and take my derivative and get e to the x, multiply both sides by the dx, and then I can now see I can replace the e to the x dx, and I can replace e to the x. So let's go ahead and try that, and I get now du is over u squared plus 1. And there's a reason for why I picked this rather than e to the 2x plus 1, because then it would have been brought in another value and everything. But I do know a substitution, or I'm sorry, I do know an antiderivative for this function that I have in here in the integral, the integrand. So what I'm going to go ahead and do is take the antiderivative of this, which should be tangent inverse of u plus some c, because we're indefinite. But because we're indefinite, we need to resub in. So my final answer will be e to the x, oops, plus c. So sometimes we have to manipulate just to make it a little easier. So I did just multiply it by 1, so that's fine. So let's go ahead and do something else where I need a trig identity substitution. And I may even have to manipulate this expression, the integrand, by splitting this into different integrals. So that's what I'm going to do first. I'm going to go ahead and split this into 2 different integrals. And see if that got me any further. So then from here, I'm looking at maybe the secant, and maybe I can replace this secant with an identity that, remember, secant is equal to 1 over cosine. So I'm going to go ahead and replace that, and if I did that, I can then simplify this first integral into cosine squared of x dx. All right, I'm going to start, leave it from there. And then this other one, I'm going to do the same thing. I'm going to change secant into 1 over cosine and simplify that so I can get sine cubed of x times cosine of x dx. All right, from here, this is where, well, wait a minute, do I need to go ahead and do anything here? Well, we have to remember some of our other formulas that we had. I have a sine or cosine squared, and we had an angle reducing formula, and they are given by, and I will write them out right here. Cosine squared of x can be substituted with 1 plus cosine 2x over 2. And I'm going to give you the sine squared of x, power reducing is that one. So I'm going to go ahead and do this trig substitution with trig identities. And we're going to have in here that this first integral will now be 1 plus cosine 2x. And then to save time, I'm just going to split this formula into 2 terms just to make it a little bit easier. All right. And then for my next one, maybe if I try to do power reducing formula with that, I still left with a sine, and it just becomes even messier. So if this is the case, I may want to, because I know sine and cosine, one is the derivative of the other, I might be able to do u substitution. So I'm going to go ahead and let u be sine x and take the derivative, which would be cosine x, move my dx over. I can now replace these. So this second integral is going to be u cubed du. So I went ahead and I made that simplified. It is indefinite. I will have to resubstitute that one. So my next line, I'm going to break this into two integrals. All right. So now, at this point, with everything I have, I can definitely take the antiderivative of it. So for the first integral, I will have 1/2 x. For the second integral, I'm going to have 1/2, and then the antiderivative cosine is sine, and then I have that whole anti-chain rule thing going, so I'm going to have to divide by 2. And then this last one, I'm going to do the exponential, I'm sorry, not exponential, but a power rule. And then I'm going to have plus c at the end. So a couple of things. I need to neaten up that middle term with 1/2 times the 1/2, and I'm going to have to resubstitute in for the u. So my final answer on this one will be this. So all it is reviewing basic ideas. We're going to need to review trig identities and figuring out how to manipulate these in order to take the antiderivatives. We have another one where I might need to do division. And so what I want to do is I see a quadratic trinomial being divided by a linear term. So what I want to do is synthetic division. I'm going to take the numerator and set up my synthetic division. Remember, it's the coefficients. Remember, they have to be in the order. And remember that if there is one term missing, like if the 2x was missing, I have to fill in a placeholder of 0. Remember, we're always going to divide by r. And remember that denominator or our divisor is going to be always x minus r. So it's always the opposite value of r than you think. So, and oops, I had the wrong number there. It should be -4 I'm dividing by. So from here, I'm going to go ahead. Remember, in synthetic division, your first term always comes down. And then you multiply the two. So -4 times 1. Add it to the second column. We're going to add. We multiply -4 times -2. Add it to the next column. Add. And then our answer this, remember, this is always a remainder. So this is going to be x minus 2 plus my remainder, which is always written over the divisor. And it seems a little silly to do this, but what if I can replace this saying this is being divided and I can now have this answer left. So in this integral, I now technically have this. And what I'm going to do is I'm going to split this into two different integrals. I'm going to do the x minus 2 and I'm going to add the 7 over the x plus 4 dx. And this becomes much easier to take the antiderivative of. So for the first integral, it should be x squared divided by 2 minus 2x. The antiderivative of this one, if I factored out that 7, I would have 1 over the x plus 4. Obviously, then we're going to do ln equals or ln of the absolute value of x plus 4, and then plus c. So this would be the final answer. And if you cannot remember this antiderivative, you can always do u substitution and see that that's what you would get. So this one is our answer for this, and we used synthetic division. So then I have one where we're going to have to complete the square. Completing the square, we have to remember, we learned basically, if we were given something like this, that was not a perfect square trinomial, then we have to complete the square by getting this out of the way. But the problem is I don't have an equation. So whatever we would do, we would also, remember, take half of this middle term, So we would say 4 divided by 2, and then we would square it, or ended up being 4. I would have to make sure this one's out of the way. We would add that perfect square to both sides. So I would have to add 4 to both sides. Now, perfect square trinomial, I can go ahead and do this, combining like terms here. So this is how we would solve it by completing the square. But what I want to do in order for this integral is I have to do it all on the same side. So it's kind of like saying I have to pretend there's no equal sign. But I can still do the same process by just moving my constant over to the side. Put it out in the boonies for the time being. And then remember, we would take half of this square, it should be, I'm adding 4. But because I'm only doing it to one side, technically, you have to keep the balance by going ahead and doing this plus 4 minus 4. You're going to basically add 0 in. But we're manipulating it so that when I want, I can now take the first 3 terms and say, oh, it's a perfect square trinomial, and I can factor it. Then I'm going to go ahead and combine these. And then that's what I would have on the other side. If I was going to have it equal to, I would move that 1 over. But now I can do this all on one side, and that's technically what I'm going to do in this integral for under the radical. I'm going to complete that square and make it look like something like this, okay? Because if I can, this could be, looks like sine inverse for my antiderivative. So what I'm going to do is I'm going to go ahead and complete the square for this denominator's radicand. So I got negative, what I'm going to do is I'm going to factor out a negative 1 first. And I can get a positive x squared plus 8x plus 7. And then if I want to manipulate that, I'm going to do my work over here real quick so I don't have to keep writing the integral. If I have this negative 1, I'm going to go ahead and try to complete the square. I'm going to stick my constant out in the boonies. I'm going to take half of the b term, or the linear term, which is 8 divided by 2 is 4. 4 squared is 16. I'm going to add 16 and subtract 16. So I'm really adding 0. So then I can go ahead now and then say these 3 terms is a perfect square trinomial. And then I'm going to combine these 2, which would be negative 9. Let's do brackets. All right, so now I'm going to go ahead and distribute this negative back in, and I'll get positive 9 minus this. So then I'm going to go ahead and replace this into my integral. You could do u substitution to get rid of that x plus 4, so you should have 9 minus u squared if you wanted to, if you know the pattern. We can then definitely see that the antiderivative of this would be sine inverse. So I do get sine inverse. And technically, if you remember the formula, we can go for it. But if you don't, I'll do this real quick. So that I would, oops, let me, before I do this, let's do this one. I would have du and then the square root of 9 minus u squared. Okay, easier to see. So then remembering the antiderivative of this would be u divided by 3 plus c, and then I have to do my resubstitution. So if you can avoid the, doing that and you see the pattern, that's awesome. And this would be my final answer. So this became using completing the square in order to solve this integral. One more problem. We want to be able to use the conjugate. So on this one, I'm going to multiply by its conjugate. Remember, it's just 1. So I'm going to be multiplied by this. And there's a reason I like to do that, if you remember from trig, is if I want some form of this identity, and then I can go ahead and do substitution with that. So if I do the conjugate, I know then I'm going to get 1 minus cosine x over 1 minus cosine squared of x. And then I can do my substitution with sine squared, like that. And then from here, I want to split these into two integrals, and it becomes much easier to find the antiderivative. And then from here, I'm going to go ahead and say that this is really cosecant squared of x, using another trig substitution, the reciprocal. And then I have minus, and I'm going to go ahead, this is really looks like cosecant squared of x cotangent x. And from here, we can go ahead and take the antiderivative. It should be negative cotangent x minus, and then a negative cosecant x plus c. So I got to have a negative times a negative. My last step is just make that middle term positive. And I am done.